Yes, yes.
Okay. Hello and welcome to the New York City Category Theory Seminar. Today we're going to speak to an old friend, Saeed Salehi, from the Tarbiz in Iran, and he's going to talk about self-reference and diagonalization, their difference and a short history. Saeed, we have a little tradition here in this seminar. You have to tell us where you were born, 4 things. Where you were born, where you did your undergraduate degree, where you did your PhD, and where you are now. Take it away, Saeed.
Okay. Well, thanks a lot. Hello, everybody. And first, I would like to thank the organizer, Noson, for inviting me to deliver a talk here. Well, about your 4 questions and your tradition, let's say, I was born in Iran in a city called Damghan, which is a small city, just because my parents had moved there for my father's job. And I did my undergraduate studies in Tehran, Sharif University. I studied pure mathematics. And then for my PhD, I studied in Warsaw, Poland, Polish Academy of Sciences. I studied mathematical logic. And in the University of Turku, Finland, I studied theoretical computer science. Now I am working in Tabriz, which is my hometown actually, because I studied my school years all in Tabriz, and then for university studies I moved to Tehran and then to Poland and Finland, and then I came back to Tabriz, of course. Who
did you work with in Poland?
Please.
Sorry.
With Zofia Adamovich, who was present in my MOPA talk in New York. And in Finland, I worked under the late Professor Magnus Stenbo. It is spelled Stenbo. He was a Swedish-Finnish professor.
Very nice. Thank you.
Thanks a lot. Well, here I have the message that your internet connection is unstable. So I am hoping that everything will go fine and you will see my pages smoothly. Well, the title of my talk is Self-Reference and Diagonalization. Yeah, yes?
Yeah, the internet's working. It seems to be working. Go.
Well, I'm just praying that it will keep working for this 1 hour and a half. So when Noson kindly invited me to deliver a talk, well, the first thing that came to my mind was that, well, I should talk about diagonalization because it had occupied my mind for the last, I would say, year and more, at least a year and a half. And then when he kindly reminded me and some other speakers to send title and abstract, I thought that, well, I can also talk about self-reference and diagonalization. And then when I started to prepare the slides, I thought that, well, maybe I can add fixed points also. So I will talk about fixed points, diagonalization, and self-reference. Well, let me say that preparing these slides took me quite a lot of time. Well, I can say more than usual for many reasons, but one of the reasons was that I was learning a lot on the way, as you will see here, and it took some time, well, as long as preparing for a whole paper. So let me start from what I mean, or what I understand by fixed points, diagonalization, and self-reference. People use these expressions interchangeably, but we will see that there are some little differences between them. When we say fixed points, we mean that there is a mapping. There should be a mapping. Sometimes people call fixed points, but without there being any mapping. But when we say fixed points, there should be a mapping and an object, which is proved to exist and is mapped to itself under that mapping, either in the theorem or in the proof. So this is let's say, precise definition of what we understand by fixed points in mathematics, also in category theory or any other science. By diagonalization, well, diagonalization has been used in many different contexts without having a good definition, a precise mathematically cut-edge definition. Well, let's define this. This is actually a proposal, and you are all welcome to disagree or debate on this. When we say diagonalization, we mean that the diagonal of a matrix is used or referred to in the theorem or in the proof. So we should have a matrix, and we should refer to its diagonal in the proof or in the theorem. Well, what's self-reference or circularity? Well, I haven't included circularity because circularity is more of a philosophical notion, but well, and I'm not sure if it is synonymous with self-reference. But when we say self-reference, we understand that something, which could be an object or even a concept, refers to itself. It may refer to its code or its name or something of itself, again, either in the theorem or in the proof. Well, let's start with an example of self-referential theorem and proof. Well, Barber's paradox, which is a theorem in first-order logic. If we have a binary relation of shaving, okay, we can prove in first-order logic that there is no Barber such that for all x ranges among the persons, Barber shaves X if and only if X doesn't shave himself, or X doesn't shave X. Well, proof, if there is such a Barber, then for X equal to Barber, here comes self-reference, refers to itself. We get the contradiction that Barber shaves Barber if and only if Barber doesn't shave Barber. And this is, this biconditional is similar to liar's paradox. Liar's paradox says that I am false, or I say lie. I say a lie. So it's a sentence such as lambda, such that lambda if and only if not lambda, okay, which is a contradiction. So here you don't see a fixed point, right? And we can discuss, we can argue with each other if it is a fixed point theorem or not. And you don't see any diagonal, you don't see any matrix here. So we can discuss if it is a diagonal argument or it's a fixed point theorem or not. In second order logic, you can prove even more that there is no binary relation and an object such that for all x, that object is related to x if and only if x is not related to itself. Again, the same proof works here, and this is a theorem, which is self-referential. But this being self-referential or not is not easy because when we come to the question of if Yablow's paradox is self-referential or not, we have had many bloody discussions, actually bloody battles among philosophers that if that Yablow's paradox was self-referential or not. But that's a long discussion and requires one or even more other talks. So I do not enter to that topic here, but I just warn that being self-referential is not an easy matter, at least for Yablow's paradox. So let's see some fixed points. We saw that by fixed point, we mean a mapping and an object which proves to exist that is mapped to itself. For example, Lavier's fixed point theorem in category theory, which says that in a Cartesian closed category, if there is a point surjective map from B to the A to the power of B for objects A and B, then every map from A to A has a fixed point. By fixed point, well, we can say that a mapping from one, the terminal object to A, such that S is equal to f of S. Or Knaster-Tarski's theorem that says that every monotonic function on a complete lattice has some fixed points, and those fixed points constitute a complete lattice. Or Killinghis fixed point theorem, every Scott continuous function on a directed complete partial order with a least element has a least fixed point. So here we can discuss if these fixed points are self-referential or are diagonal or not. For Killinghis, actually, we have another theorem, Killinghis recursion theorem in recursion theory, which is called fixed points sometimes, but I would like to start my discussion with this one. Let's look at Killinghis recursion theorem, which has two readings in the literature. The original one says that for every computable f, the big F on x and vector y, there is an index e such that the function with code e is the same as f on e and after vector y. This, okay, I cannot highlight here if you see this. This symbol means that either these two functions are undefined or they are defined and have the same value. So they are equal as partial functions. The second reading is that for every computable f, there is an index e such that e and fe code the same recursive function. Well, its proof is a good example of a diagonal argument. By the SMN theorem, we have a function s of I and j such that s of I and j is a recursive index of this function, which maps y vector to the phi I of j and y vector. And now we consider this matrix f of s of a and j and vector y for I and j in N, and it's diagonal, which maps x and y vector to this one, f of s of x and y vector. This diagonal is a mapping by itself, is a recursive function, and so it has an index such as m. Now we put e to be equal to s of m and m. Here you can see a kind of diagonal argument. Now if we unpack these old definitions of e and s and m, then we prove this Killinghis recursion theorem in one line. Actually, it has a very short proof. So is this a fixed point or not? Well, here e and f of e may not be equal to each other. F could be, for example, f of x could be x plus 1. It has no fixed point. So they are not, e is not a fixed point of fe, they just quote the same function. Now, if we look at the functions, for example, let's say we have a recursive function h and map it to this function that we decode h to get a code of h, and then we map h to the recursive function with the code whose code is f of the code of h. So this mapping, if it is a mapping, has a fixed point actually. This there is a fixed point by this proof, which is g, for example, g equal to the phi of g. And if we let e to be the code of g, then we are done. We have proved this one. But this phi is not a really mapping, is not a well-defined, unless, you see, here we decode h, unless we have this condition that if I and j code the same function, then f of a I and then f of j code the same function too. If f does not have this property, then this is not a function. This is not well defined. You see here, because h could have two codes, for example, I and j, and phi of fi and phi of fj could not be the same. So if they are not the same, so this does not define a function, a mapping from functions to functions. So if this property does not hold, then we do not have a mapping such that we have a fixed point for that mapping, and then E is the code of that fixed point. So it is not actually mathematically precise to call this theorem a fixed point theorem, but as we saw here, the proof actually is diagonal, of course, and self-referential. Self-referential comes here, the S of M and M. So we can argue that it is not a really fixed point theorem. And diagonalization. Well, we all know what diagonalization means. And actually, the main part of my talk starts from here. I define diagonalization to be an argument such that the diagonal of a matrix is used or referred to in the theorem or in the proof. There is some discussion in the literature and on the internet. You can find that asks who invented or discovered the diagonalization. Well, this inventing or discovering is an old philosophical problem here. We do not know yet if mathematics is invented or discovered. This is another discussion. And the diagonalization, we can ask who invented it. Was it George Cantor or Paul Du Bois-Reymond, a mathematical analysis actually some years older than Cantor? There is some discussion on the net which says that Raymond used diagonalization in this sense. He considered a sequence of functions f1, f2, f3, and so on, and he considered the fn of n, a kind of the diagonal, and he used it to show a new function which, for example, grows slower than all the functions on the matrix. Or there is a discussion also about René Descartes in the 17th century, that did Descartes make a diagonal argument? There is a very new paper published this year in the Journal of Philosophical Logic that his famous argument, I think, therefore I am, is it diagonal or not? Or I will show you an example of Euclid of Alexandria, this infinitude of the prime, if it is a diagonal or not. And I saw somewhere that even Pythagoras maybe invented the diagonal method. Pythagoras proves that there are infinitely many natural numbers. By this proof that if we have natural numbers 1, 2, 3 till n, then we have a new natural number which is not equal to any of them, and that is n plus 1. Well, this is my belief that I have written here, that if diagonalization was not invented or discovered by George Cantor, it was surely matured by him in a way that everyone after him, including Bertrand Russell, Kurt Gödel, Alan Turing, and Stephen Killinghis, followed his footsteps. Of course, this is a big claim, and I should provide much more evidence for that, but actually, I will concentrate my talk on other aspects. Well, let's see an ancient diagonalization, let's say, and decide actually if this is a diagonalization or not. Well, there's an ancient theorem that there are infinitely many primes, and maybe say the first historical proof goes like this, that for every finite number of primes, p1, p2, pn, there is a prime distinct from these ones. Well, this is a typical diagonal proof. And what we have seen in diagonal arguments goes like this, that for every, for example, for a countable many functions, f1, f2, fn, there is a function which is not equal to any of them. But how to find that prime which is distinct from p1, p2, and pn? Well, it can be any prime factor of this number, 1 plus the product of p1, p2, and pn. And so, since this number is not divisible by any of p1, any of pi's, because it has a remainder 1 if we divide by pi, then it should have a prime factor which should be different from any of these ones. Well, it is not clear, it is not immediate that this is a diagonal argument, but a similar proof is surely diagonal because I define a matrix and use its diagonal. Let's define the matrix A and M as follows. Let A of nm be 1 if all the prime factors of m factorial plus 1. We know what factorial is. Factorial is the product of all numbers less than or equal to n. If all the prime factors of m factorial plus 1 are less than or equal to n, and let A of n and m be 0 otherwise, if some prime factor of n factorial plus 1 is greater than n. So if all the primes are less than or equal to big N, or big N is an upper bound for all the primes, then the nth row in this matrix is all 1, because all the prime factors of any number are less than or equal to big N. So the nth row is all 1. But the diagonal is all 0, because there is no factor of n factorial plus 1 that can be less than or equal to n. You see, any number which is less than or equal to n divides n factorial, so it cannot divide n factorial plus 1. Okay, so the diagonal is all 0, and so no row can be all 1. So there is no upper bound for the prime numbers, and so there must be infinitely many prime numbers. Well, here you may wonder that, well, that then all proofs can be said to be diagonal, but it is not like that. Let's see another proof, which is surely non-diagonal. For every big N, consider these n numbers, n factorial plus 1, 2n factorial plus 1, and n times n factorial plus 1. These numbers are used in Gödel's beta function in his incompleteness theorem in 1931. I don't know if he or even anybody before him realized that this actually gives another proof for the infinitude of the primes. I haven't checked the literature. But anyway, he used these n numbers because they are pairwise coprime. You can show it easily that any two of them are coprime and cannot have any any common factor, actually. So the number of primes cannot be less than n by the pigeonhole principle. And we can actually, we can agree that if you don't see it clearly, we can agree that the proofs by the pigeonhole principle are not diagonal usually, or proofs by induction also. So it is not fair to say that every proof can be turned to be a diagonal proof. But here, actually, we see two different proofs. These are really different proofs, one of which is really diagonal. The other one is not diagonal. And about this one, I'm not sure if it is really diagonal or not. It's open to discussion. Okay, so one of the questions, or let me say, misunderstandings, actually, I can see on the net, is that how was the Cantor, let's say Cantor's diagonalization. Let's agree that Cantor invented diagonalization, or actually mature that at least. Diagonalization, how was it discovered or invented? Okay, actually, Cantor's diagonal argument is his third proof for the uncountability of the real numbers. Not the first, not the second, but third proof. Actually, you can also discuss that it is a fourth proof, but it is really third and not the first or second, actually. So let's prove that the open interval of 0 and 1 is uncountable. Cantor has three proofs. You see from the years 1874 to 1891, here a gap of at least 17 years. So the first proof, which you can find on the net easily, goes as follows. Well, let Bm be the first two elements of this sequence, which is supposed to cover open interval of 0 and 1. Well, then B0 is the minimum of x0 and x1, and B0 is their maximum. And in inductive, Bm plus 1 less than the Bm plus 1 be the first two elements of the sequence that lie inside Bm dm. We use the technique of nested intervals in mathematical analysis. You see, Cantor is now is said to be the founding father of set theory, but he was a mathematical analyst. So we define this sequence of intervals, nested intervals. Then if we consider the limit of BMs, it lies in this open interval, which is not a member of this sequence. And then we are done. We have found a number in the interval which is not in the sequence. But why this limit is not in the sequence? Well, one of the, actually the generalized argument 5 years later by Cantor uses the fact that because this interval BN-DN misses the point xn, xn lies outside of this open interval of Bn and Dn. So these sequences are missed one by one. So we get a point which is not any in the sequence. The second proof here, actually about 10 years later, goes as follows. Let I0 be a closed subinterval. Note that it's a closed subinterval of 0 and 1 with length less than 1/2 that leaves out x0. Whenever x0 is in this interval, you can find a short interval whose length is less than 1/2 such that it leaves out x0. It misses x0. Inductively, let im plus 1 be a closed subinterval of im with length less than half of the length of im such that it leaves out the point xm plus 1. Okay, so the points are left out one by one. Then the intersection is a singleton, is a real number, okay, which is not in this list of xn's. And the third proof of the Cantor for the uncountability of the real numbers is the diagonal argument. Well, it is difficult to see how it was really discovered, but maybe its idea came like this, that for simplicity, let's ignore these numbers m/2n, which are countably many. You see, because their binary expansion is finite, okay? Real numbers other than these have infinite binary expansions, which constitute of 0 and 1s in the base 2. So write the infinite binary expansion of xn as this one, 0 point yn with superscript 0, yn with superscript 1, and so on. I have used this strange notation to emphasize that they are superscript, not the power. Okay, so we consider infinite binary expansions, not the finite ones, because you see we have ignored actually these numbers whose binary expansions are finite. Again, we put I0 to be the closed interval of 0 and 1, and inductively im plus 1 be the half of im that misses the point xm. But for simplicity, we have ignored the boundary xn's. So for example, we have this here, the interval 0, 1, and we consider x0. If x0 is in the first half, then we consider the second half, and vice versa. Now we consider x1. If x1 is not in the second half, then we are done. We consider x2. But if x1 is here in the second half, so it's either in the first subhalf or the second subhalf. So if it is in the second subhalf, we consider the first subhalf. Again, we consider x2, which is here in the second subhalf, and so on. Then again, we use this nested interval. But something happens here. You see, when x0 is in the first half, its first digit in the binary expansion is 0. So x is 0.0 and something else. x1 is in the second subhalf, so its binary expansion begins with 1. And again, in the second subhalf, its second digit is also 1, and then with some other digits of 0 and 1. And also for x2, it is in the second interval 1, the first subhalf 0, and the second subhalf 1, and so on here. So if im was chosen as BMDM, then we consider its midpoint, Cm. If xm belongs to the first half, we consider the second half. And if it is in the second half, then we consider the first half. In the first case, when xm is in the actually first half, its mth digit is 0. And in the second case, when it is in the second half, its m's actually digit in the infinite binary expansion is 1. Now again, we consider their intersection of these closed subintervals, which is a unique point, which is a singleton x. And x is not in the sequence. Actually, this is old techniques used in the past 17 years. But let's look at its binary expansion. It is 0 point, okay. X0 was in the first half, so x is in the second half, so it is it should be here 1. So it's it is the swapping actually of the first digit of x0. If it is 0, this is 1, and if it is 1, then this is 0. And the same with the other digits. So this is what we can call the anti-diagonal of this matrix here. So in our example that x lies here, we see that x is 0.100 and something else, which is the anti-diagonal. By anti-diagonal, we mean that the zeros are changed to 1 and ones are changed to 0. We swap the places. So maybe we are not sure what went in Cantor's mind. Maybe diagonalization was discovered like this by considering the binary expansion of these nested intervals that were used in the first and the second proof. Anyhow, but before going to my main topic, my main topic was the diagonalization lemma, actually, what I thought I intended to talk about. Let me mention some history. Well, Cantor's second proof is almost missing, actually. We read in a 1994 paper in the Monthly that the authors began analyzing Cantor's original articles, his 87 article that contains his first proof and 91 article that contained the diagonal one. But of course, between the 1874 and 1891, there appeared 2 other papers by Cantor, which contain proofs of the uncountability of the reals, and these are not mentioned here. And we read in another monthly paper, American Mathematical Monthly paper in 2010, that in 1874, 2 years before the publication of his famous diagonal argument, George Cantor's first proof of the uncountability of the real numbers appeared in print. And this is wrong, actually. It took 17 years, not 2 years, for Cantor to discover or invent the diagonal arguments after his first proof. And 2 other proofs, at least 1 other proof also appeared in between. But this is a paper that I strongly recommend for studying. This is just 6 pages in Mathematics magazine by John Franks. Cantor's other proofs that R is uncountable. Here, Franks mentions all 3 proofs in a very, very pleasing way, a very amusing paper, and in a correct historical context. So this is really strongly recommended for studying. So actually, let me have some other philosophical discussions here. So we can argue that fixed points imply diagonal, and every fixed point argument is a diagonal argument, and every diagonal argument is a kind of self-referential. Well, let me say that because I saw some theorems are called fixed points, but there is no mapping, and there is no fixed point of those mappings, which are called. That maybe some people call fixed points for the things that are fixed point of a relation. So, for example, maybe there is a binary relation and an object which is proved to exist and is related to itself in the theorem or in the proof. But it is not fair to call these proofs or theorems fixed points because they are self-referential. they could be fixed point of some relation, but they are not called really fixed point. It is better to call them self-referential, because if we call them fixed points, then the fixed points are equivalent with self-referential. Self-referential means something is related to itself, is referred to itself, and by that relation, by that very relation. Okay, but more generally, we can argue that every fixed point is a kind of diagonal argument. In this way, if we have a function f such that it has a fixed point and we study its fixed point, we can consider this its characteristic matrix such that a of a and j is 0 if f of a is j, and it is 1 if f of a is j, and 0 otherwise if fi is not j. And this characteristic matrix is a 0, 1 matrix. Okay, the fixed points are f are indexed on the diagonal of this matrix with entry 1. When they are 1, if it means that if it's the case, let's say, if it is a of k and k, then f of k should be k, so that its entry is 1 here. So every fixed point can be said to be a diagonal argument by this artificial matrix that we consider here, and it's diagonal. All the fixed points lie in the diagonal. And we can say that every diagonal argument is self-referential because if we have a matrix here, okay, its diagonal or the diagonal entry a of k and k relates k to itself. It is related by the entry of this matrix here. Well, actually, as I said before, you are very welcome to disagree with this or dispute this, but it is just a kind of guess or estimation. But the converse is that if every self-referential argument is a diagonal argument, or if every diagonal is a fixed point argument, we can discuss about this one. Well, is really every self-referential argument a diagonal argument? For example, then liar's paradox, which says that we have a sentence saying that I am lying. So this sentence lambda is true if and only if its negation is true. And we know that the negation of this biconditional is a propositional tautology. So if we say that it's a diagonal argument, then we should have a matrix. And our matrix has only one entry here. Everything is diagonal. And every function on a singleton is a fixed point, is a constant function. Every element is a fixed point because we have just one element. And so everything is really trivial. It is very trivially diagonal. So it is not really fair to call it a diagonal argument. Or Descartes' cogito, this cogito ergo sum, this is the Latin version. I think, therefore I am. You see, Descartes doesn't consider anybody else, only himself. I think, so I am. So the only thing that he talks about is I. If it is diagonal, the matrix has just one entry, and everything is diagonal, everything is fixed point. Or this one is more interesting. Is every diagonal fixed point? Well, if there is a function for a given matrix, if there is a function from the entries to the entries, then such that the f of the diagonal is one of the rows or one of the columns, then f has a fixed point. So we have this diagonal which comes from Lavier's paper in Category Theory 1969, and Janowski popularized it in this very interesting paper of BSL, the Bulletin of Simulacry, in 2003. Here, actually, Lavier and then Janowski showed that almost every diagonal argument that we know in the history is a fixed point one, or can be turned into a fixed point theorem. Well, actually, all of them, for all of those arguments, had a function like this, such that the f of this diagonal was one of the rows or the columns. Well, usually the rows. Okay, then we had a fixed point here. Well, for reaching to a contradiction, they considered functions which do not have any fixed point. For example, negation function, or the swapping function that I talked about that maps 0 to 1 and 1 to 0. This negation function does not have any fixed point, so we get a contradiction here. But in general, I don't know how to prove that every diagonal one is a fixed point. Every diagonal argument is a fixed point argument. But we do know that almost all of them, actually all of the ones that we know so far, are a kind of fixed points. And there is another paper that I came up with when I was preparing these slides from Bernd Bolt.
Saeed, just
should I come back?
Yeah. I just want to say in Lever's thing, one is a contrapositive of the other. In other words, it's a diagonal. There's a diagonal argument. The statement of the theorem gives you a fixed point, and the contrapositive is
yes.
If
we do not have a fixed point, then none of the rows or this is a kind of is not a f of the diagonal.
Right.
Is that it?
Right. Yes.
Okay. Thanks a lot. So we have there is a really interesting paper here, with which I do not agree. Actually, totally, but I agree with a part of it that I will explain here on fixed points, diagonalization, and self-reference in 2006. Here on page 48, Bolt says that diagonalization need not result in fixed points, and fixed points need not be self-referential. Well, I don't see why, but on the diagram that he draws on page 63, he writes that diagonalization implies fixed points. And objectual self-reference implies fixed points also. Well, you have to read the paper to see what objectual self-reference means. And by fixed points, we have incompleteness. And he mentions that Janowski 2003 shows how all the usual suspects, paradoxes, limitative results can be couched in terms of this framework. This framework is this diagram here that Noson explained that Lavier says it's a contraposition, that if f does not have a fixed point, then no f of the diagonal can be a row of this matrix. And by that framework, he means this one. And in terms of this framework, and then follow from the generalized contour theorem. Generalized contour theorem is this turning contours diagonal argument to a fixed point argument. But here, I'm sure that we are not speaking the same language with Bolt. We do not have a precise mathematical definition of what diagonalization is, what we mean by fixed points. There are fixed points of mappings or fixed points of relations, and what we mean by self-reference, objectual self-reference, or some other kinds of self-reference. Anyhow, actually, this is open to discussion, and we do not have a general agreement. But unfortunately, these three expressions, self-referential, diagonal, and fixed points, are used interchangeably without much care. And actually, we can see that there are some little subtle differences here. But for mathematics, it does not matter really. So this is really what I wanted to talk about, this diagonal lemma of Gödel and Carnap. This lemma is explained popularly in the literature as follows. Here I quote Smorensky in a very new paper, which is online and it does not have any page numbers yet. But by quoting Smorensky, I do not want to actually disagree with him or say that he's wrong, because I want to point out that there is a big misunderstanding. And Smorensky is one of the authorities of diagonal lemma and of self-reference in arithmetic. He has written a very good paper in 1981, 50 years of self-reference in arithmetic, and another one in 1991, the development of self-reference, Loeb's theorem. This is a book chapter. So Smolinsky is an authority here, or let's say like this. And he writes in this very new paper that linguistic self-reference goes back at least as far as the Greeks to a variant of the liar paradox. Self-reference in formal languages, however, originated in Gödel's paper of 1931. I agree with these ones. In it, as we know, he presented the construction for a formula, not PR, probability in PM, Principia Mathematica, of a sentence phi such that PM proves that phi is equivalent to the not probability of phi. I do not agree with this red one. I will explain why. He also noted that the construction held for any extension T of PM, which was primitively recursively axiomatized. So this is what we are grown up with. We are actually, we all believe that Gödel constructed a sentence phi such that it is equivalent to its unprovability, and it is all wrong. Let's look at Gödel's original paper here. He uses something like this. It is his notation, substitution of y, in which the free variable with code 19 is replaced with the code of y. We can call it diagonal today. Let's write diag y for this one, which results from substituting. Actually, Gödel's had one free variable, but we can also substitute all the free variables of y with the Gödel code of y. Then Gödel uses this binary relation, q, x, and y. Let q, x, and y say that x is not a proof code for the diagonal of y. This appears on page 175 of this collected works. Since q is primitive recursive, he called them recursive, but now we know that they are primitive recursive. There is a formula he called relation signs q, such that if M is not a proof code for the diagonal of M, then Principia Mathematica proves the Q of M bar and N bar. M bar is a term that represents the natural number M. So is N bar. And if M is a proof code for the diagonal of N, then PM proves the not Q of M bar and M bar. These are equations 9 and 10 on this page of Gödel's paper. Then he lets py to be for all x, q, x, and y, and puts Rx to be q of x and the code of py. You see here he diagonalizes q. Then we have the diagonal of p is that, you see, we put the code of p in the place of the free variable of p. The diagonal of p is that for all x, q of x, and the code of p, which is for all x, Rx. X is defined like this. And this is what we call today G, the Gödel sentence. The Gödel sentence is this one. So also we have that Q of M and the code of P here by definition is R of M. Now if we can translate 9 and 10, when we put N to be the code of P as follows. If M is not a proof code for G, which is for all x, Rx, then T proves R of M. Here we have put N to be equal to the code of P. And if M is a proof code for G, then T proves not R of M. And these are all the diagonalization that Gödel uses. By this, you can prove that T doesn't prove G, and if it is consistent, and it doesn't prove not G if it is omega consistent. Because if T proved G, let M be its code. So M is a proof code for G. Then we have that T proves not Rm. But if T proves G, then T proves for all x, Rx. So T cannot be consistent here. If T proves for all x, Rx, it should also prove Rm and not the negation of Rm. And also, if T proves not G, then T proves not for all x, Rx by definition. Since T is consistent, then if T proves not G, then T doesn't prove G. So for every M, M is not a proof code for G. So T proves Rm. So T proves Rm for every M, and T proves not for all x, Rx. And this is exactly the definition of omega inconsistency. Actually, Gödel defined omega consistency to actually contradict these two conditions together. This is all Gödel's proof of his first incompleteness theorem, really compacted in one page. So what happened to this one that we are used to it? But Gödel never proves that his sentence is equivalent to the not provability of itself, provability in PM or Q or anything else. The question is, did Gödel have a formula pi x for proof predicate such that if M is a proof code for psi, then Principia Mathematica proves pi of M and psi, and if M is not a proof code, then PM proves not pi of M and psi. No. And then if even he had this pi, could he show that his sentence G is equivalent to the not provability of G, that G is equivalent to the non-existence of a proof code for G? Well, actually, I believe that this is not the case, but I haven't been able to prove it. So if I prove that, if I manage to prove that, then I can show that this belief of everybody is actually false. Gödel never had this biconditional in his paper, not even he but also his successors, like Russell, Killinghis. I will show one by one that they did not use this biconditional. But if we start from pi, from probability predicate, then we can put PR of y to be for exist x such that x is a proof code for y. But then the diag is not a function symbol in our language, so we need a formula delta x and y that strongly represents it, in the sense that if M is the code of the diagonal of phi, in which all the variables are replaced with the Gödel code of phi, then PM proves this sentence, which is stronger than by representing it. By representing means that if it holds, then the theory proves it, and if it doesn't hold, the theory proves its negation. And of course, in this case, if M is not the code of the diagonal, then PM proves that the not of delta of M and phi holds. If M is the code of that diagonalization, then PM proves the delta of M and phi. And also this is stronger one. Then if we let Q to be this one, that the diagonalization is not provable for all Z, such as Z is the diagonalization of Y, there is no, X is not a proof code for Z, then yes, PM can prove this for Gödel's sentence. So for Gödel to be able to show this equivalence that we believe that he proved, but he didn't, we need some other things here, at least representability of this diagonal function, which is primitive recursive actually, because our coding is primitive recursive. But otherwise, well, I do suspect that for all Gödel had, it is really difficult or even impossible, let me say, that to prove it. So the diagonal lemma is credited to Gödel and Carnap more generally. Carnap proved it in 1934 in the book, which is translated to English in 1937, The Logical Syntax of Language. I have just quoted it to show that how difficult it is to read. Actually, I read it very fast, but I confess that I don't understand some of the expressions. Actually, I have forgotten some of them. But anyway, let's see that this is the very first diagonal lemma that we know today. How it appeared in print for the first time, actually in English. Let any syntactical property of expressions be chosen. Let G1 be the sentence with the free variable x, for which we will take the term number 3, which expresses this property. Let G2 be that sentence which results from G1. If for x, substitution of x3 string x is substituted, so you see a kind of diagonal here. Thus, if G2 is given, the series number of G2, this means Gödel code of G2 can be calculated. Let it be designated by B. B is a defined ZZ. or maybe a well-defined number, I don't know. Let the Sn, maybe a standard sentence, substitution of B for 3 with substring B, BG3. Thus, G3 is the sentence which results from G2 when the GT with the value B is substituted for X. It is easy to see that, well, not really easy, but it was easy for Carnap to see that syntactically interpreted G3 means that G3 itself has the chosen syntactical property. Oh, a really difficult text. Anyhow, so let's see what was really Gödel diagonal or self-referential lemma. For Gödel, it was only this one, that there exists a formula Rx such that for every natural number, if M is not a T-proof code for all X Rx, then T-proofs are M. And if M is a T-proof code for all X Rx, then T-proofs not Rm. These two are sufficient to show that T doesn't prove for all X Rx if T is consistent, and doesn't prove its negation if it is omega consistent. For Carnap, what he showed was that for every formula f(x), there is a sentence sigma such that sigma is true if and only if f of the code of sigma is true. This is what we call semantic diagonal lemma these days. So you see that these are not really similar. And this biconditional doesn't appear in any of Russell's paper in 1963 or 36 or 37 or 39, neither in Kreisel's paper 50 or 53, not even in Henkin's 52 paper and Loeb's 55 paper, and not even in this book of Tarski, Mostovsky, Robinson, which was published in 1953 and reprinted in 68, 71, and in 2010 by Dover Publications. It was actually written between 1938 and 1939. A hint of this, this biconditional appears in Mostovsky 1952, but the first explicit biconditional appears in Pfefferman 1960. I could not find any paper before Pfefferman that mentions or uses this biconditional. What we are used to today was actually started in the literature, as far as I could see, in 1960. You see a kind of 30 years after Gödel. And after that, everyone follows the suit. Montag in 1962, Kreisel Takuti 74, Smolinsky's paper in the Handbook of Mathematical Logic 77, and so on. Now everybody believes that this biconditional was in Gödel's paper or even in Carnap's book, but not, and not even these classical works after Gödel's. We are used to believe that, actually, but historically speaking, it was not formulated like this. And I hope to be able to show that these are really different. So I have half an hour, but I don't want to read all this. So just to show really some history, that Russell's paper in 1939 presents an informal exposition of proofs of Gödel's theorem and Church's theorem in JSL. And here you see how he actually presents diagonal lemma as his lemma 1. And well, unfortunately, Russell here doesn't mention Carnap, and Smolinsky wonders in his paper why he doesn't do so. But maybe there could be some historical reasons that we don't know. But anyway, this is what Russell actually, or many people, thought about Diagonal's lemma at that time. Let X has the property Q be expressible in L, the language L, then for suitable L. Suitable means that we can express this formula, which is a kind of substitution formula, I will explain later, can be found a sentence. He says formula, but means sentence f of L with the number n, with Gödel number n, such that f expresses n has the property Q. So f expresses f has the property P. The difference of P and Q is that the formula has property P if its number has the property Q. Q is the property of numbers and P is the property of formulas. So by suitable L, he means that this phi of x and x is expressible in L. What is phi? Phi x and y is the number of the formula got by taking the formula with the number x and replacing all occurrences of v. V is the free variable of it. In it by the term of L. He says formula, but he means term of L, which denotes the number of y. And the proof is almost the same as the proof of Carnap that we read with so much difficulty in the in earlier slides. And I do not want to read that, but I just want to show that how Gödel's original diagonal lemma was at that time. And I would like to also quote Kreisel here to see to see why was it diagonally, how what was the matrix and what was its diagonal and how it was used in Gödel's proof. He writes in this paper in Fundamenta Mathematica, 1950, that what Gödel did was to apply the diagonal definition to a system of predicates which are not systematically decidable but quantified. Now we must expect that the formal definition of the diagonal predicate is of the given sequence n of m, say the p's, then a p of p is undecidable in the system. Why? Because this situation occurs in Gödel's argument. S of a and b is a function whose value is the number of the expression got when the free variable and the expression with the number b is replaced by the number a. So this is a substitution function. Then Gödel orders expression of a formalism by his numbering so that, say, n of alpha with the free variable alpha has the number n. He considers the sequence of formula that S of m and n is provable, which will be provable if a of n m can be proved. It means that the n's formula on the m's number. So he says diagonal, but he means anti-diagonal definition of this one. Anti-diagonal means that we negate it. We consider it's diagonal. It will be for all y. There is y such that y is a proof code for S of n and n, the diagonal one. And if we negate it, then it is equivalent to this one, that for all y, y is not a code of S of n and n. So this is Gödel's sentence, actually, which says that I am not provable. No y is a proof of me. And so on. So the anti-diagonal definition is one of the sequence, and here the diagonal argument establishes undecidability. So is this the diagonal lemma really a fixed point here? This is one of the discussions that I had with Noson some time ago. And then I promised him that I will mention this in my talk. So consider this mapping that maps the sentence psi to the f of the Gödel code of psi. If we have a monotone coding, most of the codings are monotone, or let's say increasing functions. Then you see the code of the f of the code of psi will be bigger than the code of psi. Actually, the code of f of t will be bigger than t, okay? Because it increases, it has more symbols. F of something has more symbols than something, okay? Because it has f and two parentheses. So they can never be equal. F of psi, the code of psi cannot be equal to psi. Now let's consider the equivalence classes from sentences under from the equivalence classes under the relation that they are provably equivalent inside T to itself, such that F maps an equivalence class to the equivalence class of F of the code of any of those sentences. So if this mapping has a fixed point like this, then yes, we have that sigma is equivalent to the F of the code of sigma in T, because they have the same equivalence class, so they are equivalent under T. But if F is a well-defined function, for its well-definability, we should have that if phi and psi are equivalent in T, then F of their codes are also equivalent. For Gödel's, yes, we have this one. If phi and psi are equivalent, then their probabilities are equivalent, and the negation of their probabilities is equivalent too. So Gödel's diagonal lemma can be called a fixed point. It is the fixed point of this mapping, which is well defined, but not Carnap's. This is a counterexample. Let x say that x starts with the negation symbol. Let A be a negation-free sentence. Then A and not A are equivalent in logic. And h of A, the code of A is false because there is no negation sign in A, while h of not A is true because not A starts with a negation sign. So this mapping of equivalence classes to the h of their codes is not well defined. So we cannot call the Carnap's diagonal lemma a fixed point lemma. There is no function such that this sentence is the fixed point of that function. Yes.
Saeed, can I just ask a quick question that might not be very relevant now? This is Ramar here. Yes. But look, so this idea of monotone codings and codings in general, Gödel's numbers. But we had some talks recently, and Chaim Greifman brought to our attention that original papers of Gödel were not in the language of arithmetic. They were sort of in, this either Principia, but also some other systems for coding at some point is not really necessary. So do those arguments really depend very strongly on the fact that you have to do Gödel coding, that you have to code syntactic elements as numbers? And if you do it in some version of set theory, are they still relevant? The sort of you don't really have to deal with coding anything because formulas and sentences represent themselves as set theoretic objects. Like the very fact of monotonicity doesn't really come into play.
Oh yes, you are right. Yes, you are right. Can I answer? No, son, are you there?
Please answer. Yes.
Yeah. Well, thanks for the comment. Yes, you are right. Actually, as you said, Gödel's original paper starts with this kind of, we can say, set theoretical start, and then at the end of the paper, he adds that we can do this in arithmetic. Yes, you are right. So, well, yes, this Carnap's actually fixed point doesn't appear in his first original paper, but in later expositions, for example, Gödel 1934 paper. Well, actually, what Smolensky mentions, let me come back to these slides here. Okay, no. This one here. Actually, Gödel gives a talk in Princeton, I guess, in 1934. Okay, and which becomes a good paper later. It is famous as Gödel 1934. And Rosser, this Barclay Rosser and Stefan Killinghis write it. Okay, they just write a script of his talk, and then Gödel actually edits it and then is published in some volumes or some books, for example, Davis books, or also in his collected works, also so on. And there he actually mentions that Carnap in his book has a more general this diagonal lemma. But in this paper 1939, Rosser doesn't mention Carnap, so Smolensky wonders that he wrote these scripts of Gödel's talk, and so he should hear Carnap's name, but why he doesn't mention? I have the guess, actually, my hunch is that Gödel adds Carnap's name in a footnote in that 1934 paper. So maybe he did not mention it in his talk and then later added in the published versions. So maybe Russell didn't hear that at time. But you are absolutely right that this is not in Gödel's paper, and I agree with that. And Gödel's diagonal lemma is really fixed point for this reason. But Carnap's is not a fixed point. If we consider Carnap's diagonal lemma as in today's arithmetical terminology, then it is not a fixed point. But for Gödel, it was, and so it didn't matter if his coding was monotone or not. So actually, my guess. So what happens to the diagonal lemma then? What was it then? So we see that we have kind of two versions. I had Gödel's and Carnap's, and then everybody repeats Gödel's or Carnap's construction, mostly Carnap's here. Then we have a strong diagonal or direct self-referential lemma here, which says that in a sufficient expressive language, in a sufficient expressive, we mean that every primitive recursive function is there. We have a symbol for every primitive recursive function. For all formula with the free variable x, there is a sentence such that sigma is equal, not equivalent with, is equal exactly to the f of the code of sigma. You see, this is self-reference, this is diagonal, and this is fixed point. Everything you wish there is here. And it has a very short proof. We consider this primitive recursive function, which takes the code of a formula and gives out the code of a formula in which all the free variables are replaced with the code of phi. We put n to be the f of the diagonal of x. So we have this function in our language. Our language is sufficiently expressive. And put sigma to be the f of the diagonal of n bar. So we kind of diagonalize it here. Then sigma is the f of the code of sigma by its very definition. It appears for the first time, as far as I could see, in this paper of Yaroslav in JSL 1973, in which he says that the lemma was discovered by the referee of this paper. Well, actually, I don't know who it is, but well, I could guess maybe it was Kreisel or Pfefferman, or I'm not sure, or maybe Gödel himself. I don't know if he was alive at that time. I don't know that either. Okay. And there is another one, which is also called strong diagonal or direct self-referential, which says that there are non-standard Gödel codings. What we mean by Gödel coding, computable injections from strings to closed terms here. And as Roman said here, it is not necessarily arithmetic. We could have, for example, the language of set theory, let's say. Okay, by Gödel coding, we mean any computable injection. Okay, there are non-standard. Actually, Killinghis calls them non-standard Gödel, such that for all f, there is a sentence such that sigma is equal to the f of the Gödel, the new code of that sigma. This was first actually mentioned by Killinghis in 1975 in a footnote to this very famous paper of him, actually the late Killinghis. But the first mathematically correct construction of such a non-standard Gödel coding was done by Visser in this paper, also in the Handbook of Philosophical Logic in 1989. Its first edition is the volume 4 and these pages, and the second edition, which is what is in 2004, it is volume 11 in this edition. This is a very nice and of course very long paper of Visser, in which he also considers a paradox which is similar to Yablow's paradox, but later Yablow mentions it differently, and of course it is now famous as Yablow's paradox. Some people also call it Visser-Yablow's paradox. And again, we have a very new paper of the late Killinghis. Actually, he didn't survive to see this in print by page numbers. Gödel's theorem and direct self-reference, which is online in the Review of Symbolic Logic, in which he gives some non-standard Gödel codings for that footnote of his proof in 1975. But before him, Visser has given here and also in some other places some non-standard Gödel codings which have this property here. So this is actually the last slide. Where is the Gödel, the original Gödel-Carnap lemma? Well, what we believe today is that Gödel proved this one, but did not actually. He constructed the sentences which is equivalent to the f of the code of itself. So this is called Gödel-Carnap Diagonal Lemma. Actually, I have called like that in some of my papers, which now I see that it wasn't totally correct. We have this strong diagonal lemma. This is a really fixed point. This is not a fixed point, but this is a fixed point, diagonal and self-referential, of course. And my guess again is that Gödel-Carnap's diagonal lemma, what we know as Gödel-Carnap's argument, lies between these two. It is similar to this the construction of the direct self-reference, but not exactly that. And this is really weak one, because many sentences sigma leak in here. When we consider provable by conditionals, then we can have many sentences which have this property, but they are not necessarily the sentences that Gödel and Carnap constructed in their original papers. Again, I have reconstructed Gödel's construction here. For any given f, use some dummy variables to write it like this. Actually, proof y is not a proof code for x. Then for q, we can use this one. If we have the diagonal function in our language, Gödel had this as his disposal. He had all the primitive recursive ones, but in the arithmetical second, at the end of his paper, now that by Roman's comment, yes, in his formulation of Principia Mathematica, he did not have that one, yes. So he used this construction, but that for all w, such that w is the diagonal of z, then theta of y and w holds. Is there a question? Please interrupt. Okay. But if we have this as in our language, then we could directly use it. And then again, z is the universal closure of q under y, and then r of y is defined as diagonalization of q, and sigma or Gödel sentences for all y are y. Then we have that sigma is the diagonalization of pz. If we have this one, but if not, then the delta of the code of sigma and the code of pz is true and also provable in weak arithmetics such as q, Robinson's q. And again, we have this equality that the sigma is the equal to f of the code of sigma. But of course, if we use these constructions, then we can use the equivalence, that q proves that sigma is equivalent to the f of the code of sigma here. So, well, my belief is that the Gödel-Carnap's original construction lies between what we know today as the diagonal lemma or as the strong diagonal lemma. It was neither of them, it was in between them. But actually, it needs a rigorous proof that I very much hope that I will be able to achieve that one, or to find it somewhere. Well, thanks again for all your and for the organizers for inviting me.
Well, thank you very much, everybody.
Thanks.
Anyways, thank you, Saeed.
Thank
very
you.
Interesting.
Thanks a lot.
You've managed to disentangle everything. There's a lot of different ideas that are put together. Any comments?
Because I was disentangled.
Say again, because you were? You're right. Because
I was disentangled.
Right. It's a complicated. By the way, I always thought was struck by there's a difference between self-reference and the ability to negate yourself also. I mean, that's also something that's needed. It's very clear in the category theory that f function along the right side of that commutative square or whatever, but you need to negate. Anyways, the most shocking thing was that Carnap's thing took 30 years for people to get used to. That's absolutely shocking.
Yeah.
Anyways, Roman, any more questions? Any discussion?
Well, I have a question. I was waiting for somebody else perhaps to ask one, but I can go ahead because first of all, Saeed, thank you very much. You really have this ability to make things clear. That's very nice and it's useful. And I'm sure there's lots and lots of, as you go, and I did my undergraduate studies in the 70s, and I'm sure many things I know that I say, oh, everyone knows that. This is somehow was imposed on me, and when you go to original papers, it's not quite that. But I want to ask about this sort of, well, the use of the diagonal lemma and the Gödel's first incompleteness and Tarski's undefinability of truth. Because there is this paper of Robinson from 1963 where he gives a model theoretic proof of undefinability of truth in arithmetic, and he's very happy because he says, oh, it's a diagonal free proof. But then also he has comments after that oh, there is some version of Berry's paradox somewhere there. So there was this whole industry. I think Zofia Adamovich had some papers about it with some diagonal free proof of Berry's incompleteness. And I wondered, that so this discussion is separate. What diagonal arguments are in themselves, in essence, or self-reference, but is self-reference necessary to prove results as fundamental as Gödel's first or second incompleteness? Is there something that you're thinking about? Is there something that Kripke is saying anything about in his paper?
Oh, well, it's a very, very difficult question, and I took
yes,
note of
you.
Yeah, I noted something, and I extracted some other very interesting question that what was Tarski's opinion of and how he imagined the diagonal lemma to be. But well, actually, yes, I have seen that paper of Robinson. I have seen that paper of Adamovich that you mentioned, and I also have studied this book by Tarski, Mostovsky, Robinson that I mentioned here also. Well, it was necessary at that time, okay? So I can only guess why they tried to avoid diagonal lemma and get diagonal free proofs. One guess is that its proof is really tricky. It doesn't give you any intuition. It doesn't give you any vision. I have my own reason. My very personal reason is that if you teach this lemma and you forget your lecture notes, it will take lots of time, let's say half an hour or 1 hour to remember its proof. It's difficult to memorize it. Okay,
that
I have tried myself.
That has been my experience too.
May I ask how much it took for you to remember its proof?
No, things I never remember it. I have to keep my notes close to the
The first time actually for about 1 hour, the second round about half an hour for me, it took for me. And I have written a kind of 3 or 4 papers on diagonal lemma. So now I am getting older, of course. You can see some gray hair here. So if I miss my lecture notes, then I'm not sure if I will remember its proof or not. So it was really simple and difficult, and it also well, the first half of my talk was to convince you that it also holds for Cantor's diagonal lemma. It is elementary. We have learned diagonal arguments, Cantor's diagonal argument in high school, okay? But it took 17 years at least, or even more, for a genius like Cantor to come up with the idea, okay? So this is a question, and I put to myself to study later. So, and actually, in one of my unpublished papers, I have proved that it's a kind of weak diagonal lemma is equivalent to a version of Tarski's theorem and a version of Gödel's incompleteness theorem. So they are kind of equivalent in the sense that for proving any of them, the other one is needed, okay? But if they could do it without any diagonalization, I don't know. But I know that it took a lot of time, as you mentioned. It took really a lot of time to avoid diagonalization.
Right. So maybe a quick follow-up. But on your slides, you were talking about uncountability of the reals. But I also somewhere read that the first time when Cantor used explicitly the diagonal argument was to prove that the power set is always of greater cardinality than the set. And then there is this diagonal argument explicitly. And do you know where it sort of on the chart of the timeline? You know, so the first, so you know, because the argument, whoever was writing this, maybe this was in the paper of Frank's that you mentioned, that the first Cantor had this topological argument. He used completeness of the real line and the nesting intervals, but then independently later proves the diagonal lemma to show that the power set of a set is always uncountable, from which things is always of greater cardinality, from which uncountability of reals follows indirectly. But I didn't quite know what the chronology of those things was.
No, actually, it was the other way around.
It was the other way around, I see.
Yes. You see, this is what we have learned in high school, that you see, proving that S and PS, the power set of S, are not equinumerous or equipotent is much easier for us. Actually, easy to forget, and also easy to follow. Okay, but what Cantor did was comparing the cardinality of concrete sets. That time, set theory didn't exist. He was creating set theory. Okay, so he had N, Z, Q, the algebraic numbers, rationals, irrationals, and so on. And then, yes, he found another proof for Liouville's theorem that transcendental numbers exist, or non-algebraic numbers exist, because there are more real numbers than algebraic numbers. So many real numbers should be non-algebraic. So, and that's it. And then later, this abstract objects came to existence, and abstract sets. And then for an abstract set A, we had the power set of A and this diagonal proof. We do not have any other proof that A is not equipotent with P of A. But we have actually many proofs, but they are all diagonal, I would say. And one of my projects in the future is to collect a kind of, have a collection of these proofs, which are, all of them, I can say, are diagonal in nature. Noson, are you still recording?
Yes. Would you want me to stop, or?
It's okay. It's okay.
Yeah.
No. It's okay. So let me say one of my actually this is interesting for you, reasons or motivations that why I did this study. Actually, I studied a lot. Well, I wrote a short paper, okay, on diagonal lemma, and I got two very angry referee reports. One of them by one of top experts. Okay, actually, I know both of them. One of them is young. One of them is a senior top researcher in the field, actually. So I came to this conclusion that if they don't know that Gödel didn't construct this biconditional that everybody talks about, everybody, including Smorinsky and almost everybody else, then nobody knows. So I should make it clear to myself that this was not a biconditional. This diagonal lemma was not biconditional. And the biconditional came to existence after 60s, 30 years after Gödel's. And for many years, as you, let me show it here. For many years here, okay, there was no biconditional in the literature, not in any book or any paper. Well, you can censor it, not on this part later.
No.
No.
No. Yeah, it's very interesting. No, I'm also one of those people that didn't know it. Can I just go back to Roman's question about that? One of the things I was pestering Saeed to give a talk about was to try to disentangle all the non-standard proofs of Gödel's second incompleteness theorem, Smorinsky's proof in the handbook, which Roman was the first person to show that out to me, because that also has a feeling of self-reference and diagonal, but it's different. It's totally different.
Yes.
Anyways, but Saeed didn't want to give that talk. Anyways, any other questions? Any other comments?
Yes, if I may. I was wondering about Turing, how you fit Turing's work into this categorization of the different kinds of arguments, because he would have been earlier than Carnap or Rosser, possibly.
Yes, very good question. Very good question. So let me remember Turing's proof and where the diagonal is inside it. So he used it, he did this, he did this, and then he went on, and then, okay. Well, what all I can say is that Gödel used the diagonal arguments, okay, but not in this sense, not in equivalence sense or Carnap's original sense. Diagonal in his proof was that he had this universal Turing machine, which took input the code of other machines, okay, and simulated them like that, and then he gave the code of that machine to itself as an input and observed its output. So this part is diagonal, that you give the code of itself to as an input to that algorithm and see the output here. But in this context, I don't see any connection yet. But also he proves Church theorem about Entscheidung's problem, the undecidability of first-order logic. Well, I don't see any connection in this context here. But his proof was diagonal in a more general sense, not using really diagonal lemma, but I should look deeply into it. So am I clear here? His proof is diagonal in Cantor sense, but he doesn't use Gödel-Carnap's diagonal lemma explicitly, as far as I know.
Yeah, thanks.
You're welcome.
Do we know what influenced Turing? I mean, Turing clearly knew Cantor. Did he study Gödel's original paper? Do we know?
I don't know. I don't know.
I mean, they lived in the same town. They were in the same.
Turing and Gödel?
They were both they overlapped in Princeton.
Yes, and Gödel also mentioned in his writings that he is very satisfied with Gödel's definition of what we call today Turing machines as a model for computability. Right. I guess that Turing, actually, I cannot remember the reference, but I read somewhere that Turing read Gödel's paper. Oh, yes, I remember that. Okay, so I can answer you like this, that Turing knew that, what I remember. Turing knew that Gödel proved his incompleteness theorem, okay? And he did not quite understand it, Gödel's proof, okay? And he knew that Gödel did not answer the Entscheidung's problem, the decidability of first-order logic. So he sat down to settle that problem for himself. And of course, as we know, the rest is the history. And we know that he and the Church proved the undecidability of the first-order logic, almost together, almost. So now I remember that, yes, he saw the paper, but he didn't quite understand it. But he knew that his theorem, Gödel's theorem, did not answer the decidability question. Today we know it because we have this finitely axiomatizable theory Q, Robinson's arithmetic, which implies Church theorem, the undecidability of first-order logic. But Turing's Principia Mathematica was not finitely axiomatizable that time.
Thank you. Thank you.
You're welcome. Can I have a comment also about your request about this Gödel's second theorem?
Yeah, please.
You see, one of the reasons that I did not want to talk about that was that many years ago, many years ago, when I was a PhD student in Poland and I was studying logic, I had a collection of different proofs for Gödel's second theorem. I had a very nice collection, okay? And well, that time, yes, I could talk. I could list these theorems and maybe say some interesting things, historical, mathematical, and so on. Well, then one of the tragic things that happened that I lost my notes, okay? And I am not updated them because many things has happened during these 20 years or something. And updating myself would take me some time. And I was more interested in this diagonal thing, and because and also I was first kind of offended by those two angry referee reports, but then when now I am calm that almost nobody knows the history, and we are misled by this beautiful thing, this beautiful biconditional, which has appeared at 30 years actually after Gödel's.
Saeed, have you seen Henryk Kotlarski's book, the one on proof theoretic, the model theoretic methods in proof theory? That
Kotlarski's book after his death. That
right. You know, this is the book that he was. They said right. It was edited by Adamovich, Zdanowski, and Pikorajska.
Yeah,
because he collects together. He has a whole chapter on proofs, including. I don't quite remember because my favorite proof of second incompleteness is Kreisel's, the model theoretic proof. It's a beautiful proof based on the arithmetized completeness theorem. And I think this, maybe you don't have to reconstruct your whole paper, but a presentation of this with details and somehow sorting out who discovered what would be very, very useful. Because very few people know it. It seems it's actually, when I teach it, which doesn't happen often, that I prefer this model theoretic proof because this is actually something you can draw on the blackboard. You draw some trees and I think there is some diagonalization hidden there at some point. Maybe maybe the arithmetized completeness theorem is a sort of diagonalization, a theory that speaks about itself. It produces its own models. So, but anyway, I would encourage you to do that. Give a talk and write a paper.
Saeed, I encourage you also.
Thanks a lot for.
Next semester, Saeed, we're reserving you.
Thanks a lot for the encouragement and for the offer. But have you heard the name of Kikuchi or some Japanese other name? Kikuchi and his school.
Well, Kotlarski mentions Kikuchi. I have met Kikuchi long time ago in New York. So he has So all those proofs based on various paradoxes. And I wonder about but another thing I want to mention because I was at the once at Kripke's lectures here at the Graduate Center when I think he was then writing this book Road to Gödel. He was I don't think he completed the book, but there was this whole semester when we talked about incompleteness, Gödel's incompleteness, and emphasizing the fact that he has this technology of converting every set theoretic paradox into incompleteness in planned arithmetic in a setup that, it was very convincing. He showed one or two proofs like that. And then, so maybe in the list, the self-reference, and this should be the name paradox also should be somewhere there, but maybe that's what's necessary for incompleteness is some paradoxical phenomenon that then it's converted. That's really the source of incompleteness. And it's anyway, I just wanted to mention it. But Kikuchi, so Kotlarski has Kikuchi's proof in his book as well. I think it's based on various paradox.
So by mentioning Kikuchi, I wanted to say that I have read this proof of this arithmetics completeness theorem that you mentioned, but by second-hand actually writers, not the original one, not the original papers of Kreisel, but by papers of Kikuchi and his school. I know them, but can you please also mention this? Is the paper written by Kripke? You said.
Yeah, no, it was a whole book that he was working on and working. Was the title? Was a beautiful title, Road to Gödel.
Is it published or something? Or
no, I don't think it is.
Oh, sorry, but I didn't want to bother you. But
I think there's also a video on the Kripke Center with that title, Road to Gödel. It's a long lecture. It's not very clear.
Right. This one. Anyway, so but I'm typing the book that I mentioned. So this is Kotlarski's book. It was published a few years ago, and this is a model theoretic approach to proof theory. Maybe I will just put the name. He didn't write many books. He just wrote one. Many papers, but just one book. So if you Google Kotlarski, you will find the book. It's Springer, Trends in Logic, Model Theoretic Approach to Proof Theory.
Yes.
Henrik Kotlarski.
Yes. Okay. Well, thank you very much for the encouragement and for the comments and so on.
Anyways, ladies and gentlemen, it's a pleasure. Thank you, Saeed. Again, Saeed, now that we'll see you in the spring. Anyways, thank you all. The next time we're meeting is December 7th with Robert Paré is talking. So please join. Saeed, get home safe. Take care. Stay safe.
Thanks a lot. Thank you. Thanks, everybody.
Okay,
Thank you. Bye.
Take care. Thank you.